Hello friends, good afternoon and welcome to EduSite Live Lectures. Dear friends, today we are starting a new series on basics of organic chemistry and today we are conducting its introductory lecture. In this lecture, we will be talking about electronic displacements. To discuss this topic, we have with us our subject expert Dr. Pankaj Khanna. Dr. Khanna is Assistant Professor in Department of Chemistry in Acharya Narendra Dev College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Thank you so much. Hello friends. Today we will be discussing about electronic displacements. So if we are talking about organic chemistry, and we all know that organic chemistry is the chemistry of carbon and its compounds. So first of all, we should understand a few points about like why we have placed because this is the course related to maybe a preliminary course of organic chemistry at undergraduate level. So we should know that why organic compounds are placed in a separate group as such, and all the other elements of the periodic table are placed in a different group, and we study them under the concept of inorganic chemistry. This is because of the number of compounds carbon forms, and this is because of the property of carbon that it cannot donate all 4 electrons in its valence shell, and it cannot accept 4 electrons. Because it is having 4 electrons, it can complete the octet by either giving 4 electrons or by accepting 4 electrons. So neither of them is possible, and hence we have carbon as a different type of bonding than other of the elements of the periodic table. So to discuss that in a total discussion point of view, I have placed first the topic of electronic displacement. What is electronic? What are the types of electronic displacements? We would do one by one in step, but in today's part we would be first of all focusing on bonding in carbon compounds. Like I have already told you, we will be discussing this, and then we would be discussing 2 effects in this session, which are inductive effect and electromeric effect. So starting with like the preview I have already given. What do you think that carbon forms? The bonding in carbon is of which type? What is the type of bond? As I have already told you, carbon, there are 2 types of bonding which are present in any of the compounds, ionic and covalent. And ionic compounds are those which have the bonding by complete donation of electrons, like one atom gives the electron and the other atom accepts the electrons, and the complete transfer of electron is happening. The other one is covalent, where the sharing of electrons happens because of the fact that carbon cannot give completely 4 electrons or accept the complete 4 electrons because of the ionization energy and electron affinity concept you must have earlier studied at the school level. So carbon forms the covalent bond. So covalent bond means that whichever bond carbon is having is a covalent type, that is, it is primarily made of the sharing of electrons. The complete transfer of electron is not happening in this case. So what are the things which can be classified into ionic and covalent? We say that complete transfer, sodium metal gives away the electron it is having in its valence shell and completes the octet. Similarly, that electron is taken up by the chlorine and it forms chloride ion, so that its octet is also complete. It was deficient by 1 electron, hereby completing both of them and forming a bond which is ionic in nature. So we say that Na plus and Cl minus are the components, and these are attached to one another by electrostatic forces of attraction, which is basically primarily the Coulomb's law of attraction. In the covalent case, as you can see, I have placed a few examples as hydrogen, nitrogen and methane. So why I am stressing, we would be coming to that. I have distinguished between them. So covalent compounds are having, there is no complete transfer of electrons, but there is sharing of electron. Like hydrogen molecule is having 1 hydrogen, each is having 1 electron, and they both are sharing to form a bond which is the hydrogen bond, and in between there are 2 electrons which are shared by both the hydrogens. Similarly, in case of nitrogen, and in case of methane. So, in case of ionic compounds, like I have given types of bonds in only the covalent nature, because we are talking about talking right now as carbon compounds, the bonding present. So, we are talking about the covalent, but is there any type of ionic bonding? Ionic bonding is basic electrostatic force of attraction, we have already told. So, there is no further classification we can make in ionic type of bonding. The other interactions which may be present, we cannot discuss it at this level. So, we are focusing here on covalent bonds, which are different types of covalent bonds. So, in pertinence with the carbon atom or the carbon compounds, we can see that I have placed there are 3 types of carbon bonds which are present here, which may be carbon carbon, the other may be carbon hydrogen. These are the basic skeleton of any organic compound, because we say that organic compounds are made of carbon and hydrogens, carbons and hydrogens primarily, and these are the 2 types of bond present in them, and there may be other type of bond which may be CX. I have written here the CX may be with other atoms, like carbon is forming bonds with halogens, sulfur, nitrogen, phosphorus, or any other element of the periodic table. Maybe it may be metals as an organic organometallic compounds, or maybe other type of compounds where the X may be a different thing. So, what I am trying to suggest here, you can see that I have further classified these types of bond, as the main purpose of writing the types of bonds here was that carbon carbon and carbon hydrogen bonds I have placed as non-polar. So, they are non-polar bonds, carbon carbon and carbon hydrogen, and maybe as an example we can place X as a halogen here, and I am writing it as a polar bond, polar covalent bond. So, why I am saying this? Because of the fact that there is an inductive effect, or we can say that in this type of molecules, that carbon carbon bond is having a similar type of nucleus which are present, nuclei which are present, the atoms are same. So, what is happening, starting with the first of the type of effect which is called as inductive effect, I would be taking a few minutes more before going to that inductive effect, that there are homonuclear diatomic molecules like hydrogen, nitrogen, oxygen, chlorine, like this. So, what is happening in these molecules? There is no electronegativity difference between these molecules, as the atoms are same and there is no electronegativity difference, and thus we have earlier showed that carbon carbon bond is a non-polar bond. Why it is non-polar? Because there is no electronegativity difference and there is no charges which are present on each of them. Similar cases with a carbon hydrogen bond. We have placed again a carbon hydrogen bond as non-polar. Why we have placed non-polar? Because the electronegativity of carbon and electronegativity of hydrogen, although are not exactly same, but there is very less difference between carbon and hydrogen's electronegativity. So, what is happening because of electronegativity? What is this polar and non-polar issue? What is the polarization? We would be doing it inductive effect, because the pertinence is with the organic compounds we are talking about. So, we would be talking more of organic compounds in few more minutes. So, taking back to from homonuclear diatomic molecule, I would like to draw your attention towards heteronuclear molecules. As we have said that carbon hydrogen is also having a similar kind of electronegativity environment. So, methane will also be non-polar, means that there will be no electronegativity difference between carbon and hydrogen, or very less electronegativity difference, which is negligible, and thus what we are seeing, the difference now is very negligible. Comparing this with methyl chloride, methyl chloride has, or chloromethane has 3 carbon hydrogen bonds which are of again negligible electronegativity difference, but the introduction of chlorine into the carbon skeleton changes a few things. These few things are nothing but the electronegativity of chlorine is way higher than that of carbon. So, here we are talking about the polar carbon chlorine bond. What is the difference? We would be looking at this difference in a few moments. This is a methane molecule. So, I have placed a tetrahedral CH4 molecule, but although all the carbon, you should not take it as that one CH bond is different. I have depicted one CH bond as in red, and the electron density is shown as a as an elliptical orbital kind of molecular orbital kind of thing. All the 4 bonds are like the ones which is given in red, the CH bond. So, the CH bond, as you can see, if we think that, if we say that the 2 electrons between the carbon hydrogen bonds are equally shared between carbon and hydrogen, I have placed such that the ellipse is actually depicting that the density towards carbon and towards hydrogen is equal, or if there is a minimum difference because of the slight electronegativity difference, it is negligible. So, the carbon and hydrogen are equally sharing and maximum density is between them. This scenario changes as I make the carbon hydrogen bond, I turn that carbon hydrogen bond into a carbon chlorine bond. What I have done here in this slide is that the chlorine is having now not an equally shared environment, but a balloon kind of thing is happening here, and the chlorine is having much of the share of the carbon chlorine bond. So, what I am trying to suggest that when a hydrogen is replaced in methane by a more electronegative atom such as chlorine or maybe any other halogen which is having electronegativity way higher than carbon, or because we are replacing hydrogen, we may say that chlorine is having electronegativity way higher than hydrogen as a reference, then the bond is not at all now equally shared. The carbon halogen bond is more towards chlorine, as you may see in the slide that the red balloon is having a greater size at the chlorine side and a smaller side at the carbon, which is the intersection of all the CH bonds and chlorine. The point I am placing here, this is the carbon and this is the halogen. So, halogen is having more electron density, carbon is having less electronegativity, less electron density. By this, there is a generation of a positive charge. I have placed delta plus because delta shows a small amount or maybe a partial amount, which is there is no as such a plus charge or a minus charge. We would be discussing what a positive charge or a negative charge is when we discuss carbocations and carbanions in future lectures or series. This partial positive charge is because of the pulling of the electron pair which is shared between carbon and halogen towards chlorine. Because the carbon is getting a partial positive charge, chlorine, to neutralize that partial positive charge, acquires a partial negative charge. So, there is what we call as the polarization of a sigma bond. This polarization of sigma bond, due to the presence of electronegativity difference, or we can say that due to the presence of a higher electronegative atom between the two sharing atoms, is called as inductive effect. So, we may define the inductive effect as I have already told you, polarization of a sigma bond by electronegativity difference between the two atoms or groups which are present. What is now inductive effect and what are its the features of inductive effect? We would be discussing those, and the first most important point is that it is a permanent effect. What do you mean by permanent effect? Permanent effect means that the carbon and halogen bond, if I am having methyl chloride or chloromethane in a because it is a gas again, and or any other compound which is a liquid or a solid in a bottle, then the properties of the bonds are there as permanently present between a carbon and halogen, or maybe carbon and oxygen, or carbon and nitrogen. The polarization is permanent because the molecule is stable and the molecule is having that carbon halogen bond or carbon any other more electronegative bond, and this will be always having the more electronegativity towards that specific atom, maybe chlorine, nitrogen, oxygen, any other halogen which is more electronegative than carbon. So, this is a permanent effect. The second point which comes, the next point which comes is that this effect is transmitted through sigma bonds to a certain distance in a chain. So, for this an example I have placed here, that I am having say a 4 carbon system having chlorine at the first carbon present, and chlorine is pulling electrons towards itself. So, it will pull electrons towards itself, as you can see that chlorine is pulling electrons from the first carbon. So, I have placed that the electrons are getting pulled by using by arrows, and I have placed 4 such arrows in this. So, what will happen? These 4 arrows means that there is a strongest pull at the first carbon which chlorine is making by pulling the electrons from the first carbon. What will happen, as we have earlier done, there will be a generation of a partial positive charge on the first carbon. So, why I have placed this, why I am saying that transmission is happening or the inductive effect is transmitted through the chain? Because this partial positive charge which is created is delta plus, means it is a small positive charge which is created on C1 by virtue of the strongest pull of chlorine on this first carbon. Now, what is happening if I take this pulling and pushing of electrons as a currency? I given this as an example in my classes, that we are having chlorine as a very strong puller of money. So, we can take electrons as a case where we are saying that electrons are money and chlorine is pulling electrons towards itself. So, it is taking away some money from the C1 carbon. When C1 carbon is left with less amount of money, or we can say that less amount of electron density, then what will it do? It will, in the next carbon in the chain, it will pull electrons from the second carbon. This is not the case when we are having a symmetrical ethyl group. When we are having an ethyl group, then first carbon and second carbon are equally sharing the electrons, because they have the similar tendency, they have the similar properties, but by the presence of a chlorine, the C1 carbon has now become more electronegative than a normal carbon. So, you can see on the slide that the C1 carbon is having a partial positive charge, and thus it attracts the electrons from the C2 carbon, a little bit of the electrons, less than what chlorine was attracting from it, but certainly it is attracting electrons of C2-C1 bond towards itself, as it is now not a simple carbon but a partially positive charge carbon. So, it takes away the electrons from C1-C2 bond and creates a double partial positive charge. So, this double partial positive charge is on C2 is again less in amount than delta plus. I have placed 2 delta, so a slightly less positive charge. Similarly, C2 exerts pressure on C3 and takes away a few electrons density and creates a even lesser amount of partial positive charge and towards C4. Going to C4, the 4th carbon atom, the property of or the features of inductive effect diminishes because of the distance, and we can see that the pulling is getting lesser and lesser when we travel across the carbon chain. The partial positive charge goes on decreasing and the property of inductive effect diminishes. So, we cannot say that it goes on to till infinity, the number of carbon atoms we are having the exhibition of inductive effect because of the chlorine present on the first carbon atom. No, it goes till the 3rd, mostly toward the 3rd or even the very negligible amount to the 4th carbon in a chain. So, this is called as transmission effect of inductive effect. That you can note down that inductive effect is a transmission effect, also it is called as transmission effect, and it is transmitted through the carbon chain. Now, when we are having inductive effect, there are 2 types of inductive effect. Minus I as electron withdrawing, chlorine is withdrawing electrons towards itself, and creating a partial positive charge on carbon, plus I which is electron releasing. The group or an atom will give electrons and create a partial negative charge on the carbon atom. So, minus I are called as electron withdrawing groups. The order of their strength is given in such a way that the Nr3 plus, the trialkyl ammonium ion, is positively charged and it creates a maximum effect, and it is the most strongest of the minus I groups. Then Sr2 plus and so on. The halogens are in the order, they come after carboxylic acid here, and they are in the order of their electronegativity, as fluorine will be having much more electron withdrawing effect than chlorine, than bromine, and then iodine. Then come the other groups which you may have a look, and we would be using these groups in various reasoning questions. The similar case of plus I, we generally talk about plus I effect for the alkyl groups. Alkyl groups give the electron density towards the carbon atom. This may be understood on the basis of the fact that more the number of alkyl groups, more the number of methyl groups are present on a carbon, the electronegativity difference in a methyl group is towards carbon. Carbon is more electronegative, as in a scale called as 2.5 and hydrogen is 2.1. So, the electron is pulled from hydrogen towards carbon. Thus, a methyl group has greater electron density on the carbon, and this electron density is kind of donated, or electron donating group is formed, so that the next carbon which is to which methyl group is attached will be behaving as if it is having more of electron density. So, this is one case. The next case is the O minus, because O minus wants to stabilize itself, it gives electrons and the electron density is increased. The applications of inductive effect lie in the fact that electronegativity difference is nil in homoatomic molecules, and in diatomic molecules with electronegativity with difference there is a positive value. So, we can say that in most of the cases diatomic molecules undergo a homolytic cleavage, and homonuclear molecules, and heteronuclear with the electronegativity difference they undergo heterolytic cleavage by creating a positive charge particle and a negatively charged particle. There is no polarity in this bond, and there is a polarity, we have already discussed the polarization due to inductive effect, and we get a kind of this mechanism. Zero dipole moment is observed here. This is a polar molecule, so dipole moment is observed here, and an example is free radical halogenation in this case, but in this case there is SN1 mechanism in which a carbocation is formed from alkyl halide by virtue of cleavage of this bond. Further applications are, we have already studied at various levels that carbocations may differ in types as methyl, primary, secondary, tertiary. So, because of inductive effect, the methyl group we have talked about, like plus I effect it shows. So, more the number of methyl groups, more is the electron density towards this positively charged carbon, more is stabilized. So, as the number of methyl groups decreases, or from this side to this side it increases, the positive charge is more of stabilized, because methyl there is no carbon which can give plus I effect. In this case there is one methyl group which is electron donating, there are two, so it is more electron donating, this carbon charge, positive charge is decreased, and in tertiary butyl carbocation it is decreased to a maximum level. Similarly, stability of carbanions can be described as methyl, there is no alkyl group attached, so it is more stable. When I introduce a methyl group here, now the electron density is increased again and it destabilizes the carbanion, because already there is negative charge, more of electron will destabilize this group, and the ethyl carbanion is less stable than the methyl one. As we keep on increasing the methyl groups, the stability decreases further, and tertiary butyl carbanion is the least stable one. Similarly, relative acidity of carboxylic acid, we can say that carboxylate ion, the carboxylic acid is one which is giving protons to form a carboxylate ion. A carboxylate ion is said to be stabilized, if it is said to be more stabilized, then the acidity of the carboxylic acid would be greater. We would be doing, when we do in another lecture about carboxylic acids, acidity and basicity of amines, that the carboxylate ion, the greater it will be stabilized, the more is the acidity of the carboxylic acid. So, you can look at the screen that more of the stabilization of carboxylate ion, a negatively charged ion, will be happening when there is a more electronegative group, like say fluorine is present. So, it will pull the carboxylate ion electrons and stabilize it more, hence fluoroacetic acid is the most acidic among the given carboxylic acids. When the electronegativity decreases from fluorine to chlorine to bromine, the acidity decreases because the carboxylate ion is now less stabilized. Because of lesser electronegativity, the minus charge is less pulled and less stabilized. In case of formic acid, there is no such case, and hence we have placed it formic acid beyond the more electronegative halogenated carboxylic acids. Why methyl or placed here or acetic acid is less acidic than formic acid? Because methyl now not pulling as in case of halogens, but it is donating electrons to the carboxylic group. When it is giving electrons, it will be destabilizing the minus charge of the carboxylic acid, and hence it is the least acidic. The similar case will be like chlorine will be positioned at different level, and we will be having the decreased stability of carboxylate ion, and we will be having lesser acidic character of acids, or the number of chlorine atom is decreased and we are having a decreased acidity. The same you can put the case with the alkyl amines. Alkyl amines also have this kind of a behavior, that the trialkyl amine will be having higher basicity because more of the electrons will be given to the nitrogen and it will be acting as a stronger base. As the number is decreased, the electron donation decreases and the basicity is decreased in this case. So, this is all I wish to express about the inductive effect. Rest of the things we would be taking in another lecture. Thank you very much for your patience. Hello viewers, in this session we would be talking about electronic displacements, and I would be discussing about the electromeric effect first and resonance effect and hyperconjugation effect later on. So, starting with the electromeric effect, what is electromeric effect? As you would be knowing about the other effect which is called as inductive effect, which is a polarization of a sigma bond towards a more electronegative atom. On similar lines, there is a polarizability of a pi cloud which is happening due to the presence of a reagent. In case of say alkenes, we are taking here I have placed, please all of you should not confuse it as a triple bond, because this carbon-carbon sigma bond is 1 and this is the cloud of pi cloud of the second bond, which is a pi bond of alkene, which is present above and below the plane of the alkene. So, this pi cloud, when it is present as such in an alkene, it is stable enough and it is shared equally by the two carbons. But as soon as a species which is a positively charged species here, which we call as electrophile, comes and towards an alkene, this pi cloud is polarized. As you may have seen in inductive effect, this polarization or ballooning of the bond or electron density is shown for a sigma bond. So here what we are looking at is that this carbon-carbon bond, which was equally shared here, is now getting polarized towards the electrophile. This polarization is creating a partial positive charge on the carbon, and this electrophile will be trying to take up the electrons completely from the other carbon, and hence the conversion of this type of intermediate is formed, in which this carbon is completely positively charged, a carbocation is formed, and this carbon is having a bond with the electrophile. So what has happened, this polarization has ultimately led to a formation of a sigma bond between carbon and the E substituent. So this polarization of pi cloud is called as electromeric effect. It is a temporary effect, that is, it happens only when, it will not happen in a bottle of alkene or any other unsaturated compound, but only when an electrophile is approaching towards that compound. So a temporary effect you can see only in presence of the reactive species. The second point in the slide you can see is that, as in case of inductive effect, the thing was permanent, but it was within the molecule. But in this case, this thing results in a complete transfer of electrons, and we get a resultant of the reaction which has happened, and electromeric effect can be divided, as in case of inductive effect, as plus E and minus E. When the above thing I have showed for alkene, the electrophile is attaching, these electrons move away from the group. It is called as plus E effect, because the electrons are moving towards the reagent. And the example is, we are adding acids HBr, HCl, HI under Markovnikov addition. We give this type of mechanism, and we say that this reaction is happening with a plus E effect, and ultimately we get the electrophile attached to the other carbon, and we are having a positively charged carbon here. But in case of the attack on carbonyls, because the polarization is, some polarization is already existing in C double bond O group, because of the more electronegative oxygen atom pulling that pi cloud towards itself, as we see in an inductive effect for a sigma bond, this partial positive charge attracts a nucleophile here, and the electrons are moved towards the other atom or group, not towards the reagent. So electrons are added from the reagent and moving towards the other atom or the group, giving the nucleophile attaching to the partially positive charged carbon, and a negatively charged ion is formed. So more and more thing of electronegativity we talk about is not very much to be discussed, but it is a case where we show the polarization of a double bond or a triple bond, any pi cloud, in presence of a reagent. So we discuss about the electromeric effect for these two cases as plus E and minus E. So groups which are acidic adding on alkene, we say that it is plus E case, and when the nucleophiles like your Cn minus or any other nucleophile adding on carbonyl compounds, aldehydes and ketones, we say that the minus E effect is happening. So that is all about electromeric effect. The second point we are discussing today is very important one, which is called as resonance. So what is resonance? Resonance is a word which is usually used more than one places. We also hear about, like in case of physics, we hear about the resonance of the sound waves when the frequencies match. So in this case we are having a different definition of resonance. But before going to resonance, I want you to answer a few questions with yourself that you know about, like, do you know about conjugation? What is conjugation? Conjugation is the presence of alternate double and single bond. What is happening in alternate double and single bond? The pi cloud which is present in a system where double bond and single bonds are alternately present are not present at the same point of the time for every moment or every time average environment. They are delocalized. So, you should understand the term conjugation and delocalization of pi cloud, which would be clear when I talk about, like, under the topic of resonance I am discussing with you the conjugation and delocalization of pi cloud. This is the structure you are aware of, 1,3-butadiene, and I have made an orbital picture of this structure as like these all double bonds. These are single bonds with the darker line, and I have put some balloons. What are these? They are p orbitals. P orbitals which are pure p orbitals having electrons in them, and they are forming a double bond here and a double bond here. So, these two double bonds which were present here can be depicted as, a butadiene can be depicted as this. So, what is delocalization? Delocalization is something that these electrons, I am pointing on the butadiene, this double bond moves towards this place and this double bond moves towards this carbon. So, what will happen in that case? We will be having a double bondish character between this carbon-carbon bond, as I have placed in the second structure, and this black show that the orbitals are overlapping p orbitals and creating a double bond between C2 and C3 carbon rather than a C1 and C2, and a positive charge has appeared at this place and a negative charge has appeared at this place. So, the double bond, we can say that I have not drawn that structure, but this structure itself says that the double bond is all present through all the 4 bonds. So, we cannot say that this carbon C2 C3 bond is a single bond. Why? Because in this structure we are having an overlapping of pi cloud, and it depicts that this bond is also having some double bond character, and these two bonds are also having some single bond character. So, what I am trying to suggest is proven by the fact that the bond lengths of C1 and C2, this C1 and C2 are at 1.34 or that of a double bond kind of thing, but the C2 and C3 bond is having a 1.48 angstrom of bond length, which is very unnatural of a single bond, because a single bond has a bond length of 1.54 something angstrom, such that we can say that this is not the only representation of 1,3-butadiene. This structure also depicts some of the amount, not all, but some of the amount of the representation of butadiene. Why I am saying so? Because this double bond in this structure makes this bond slightly shorter than a usual single or a carbon-carbon single bond, because the bond length is coming to 1.48 rather than 1.54 angstrom. Similar case was observed. Now, coming to this, I have told you what is conjugation and how the delocalization of pi cloud happens. Now, take the example, if I am not considering benzene as the cyclohexane is going down here it is cyclohexane is written here, and there is a stability bar which is given here, the basic line of cyclohexane. The benzene we are taking, because resonance goes hand in hand with benzene. When we talk about resonance, benzene is the best example of them all. So, what is happening in resonance? The benzene, if I take as an assumption that benzene is not having any resonance, and I am calling it as cyclohexatriene. So, I can say that cyclohexane, cyclohexene, cyclohexadiene and cyclohexatriene, these are the 4 molecules. So, when the chemists discovered, they found that the heat of hydrogenation, the amount of heat released, I have put minus charge here, minus sign here, the amount of heat released from cyclohexene to cyclohexane is 120 kilojoule per mole. 1 mole of cyclohexene releases 120 kilojoule per with a mole to form cyclohexane. So they thought that if this is happening, cyclohexadiene should be having 240 kilojoule per mole it should release, and cyclohexatriene, which is an assumptive molecule instead of benzene, if we consider that there is no resonance happening, it should give 360 kilojoule per mole of energy when all the double bonds are hydrogenated to form cyclohexane. So I suppose that this is getting understood to you, and now I move from a no resonating type of structure of benzene to where the resonance is happening. So you can see that heat of hydrogenation is similar kind of structure I have placed. 120 kilojoule per mole is again 120 kilojoule per mole, but this 240 kilojoule per mole, because 1,3-butadiene type of structure undergoes conjugation and has resonance, this cyclohexadiene has stabilized a little bit, and the point I was not able to write because of the less space is that actually the amount of heat which is released on hydrogenation of cyclohexadiene is 232 kilojoule per mole rather than 240 kilojoule per mole. So we can say that the stability which more number of structures give, they are lowering the energy of cyclohexadiene slightly, such that the amount of energy which is released on hydrogenation is decreasing. This is further tried when the experiment was done on benzene. Now benzene, if it was cyclohexatriene, it should have released 360 kilojoule per mole, but actually benzene released only 209 kilojoule or so per mole. Hence benzene was not cyclohexatriene. So you cannot say that benzene is having single and double bond alternately, but all the electrons are in conjugation and we have placed as a circle here. So what is happening here, that by virtue of the phenomena which we are discussing here, which is called as resonance, benzene is getting stabilized by 150 kilojoule per mole, and this 150 kilojoule per mole is called as resonance. So why we are talking about resonance? Because benzene, now how come we showed a structure which is having all the bonds delocalized as a circle here? I have placed a circle in this cyclohexane ring because of the fact that one structure of benzene, which is a resonating structure, depicts double bond here, the other one here and the third one here. In the resonating structure, the double bonds are present at the alternative bonds. Like if I place C1, C2, C3, the double bond was C1, C2. Now here there is no double bond at C1 and C2, but C1 and C6 and C2 and C3 it is present. So I have made a resonating structure of benzene like this. So to understand what is resonance, let us move to a descriptive, because till we write in words or we understand in English language or any in our own language, Hindi mein agar baat na kare, we do not understand the meaning of the thing. So the resonance may be defined as representation of a molecule by two or more structures, or which are called as canonical forms, differing in arrangement of electrons and same arrangement of other atoms. So going back to the benzene, we are having the electronic arrangement is differing. This double bond placed at another place and all the double bonds are moving, the overall structure is remaining same. So these are the two canonical forms of benzene. What I have told by virtue of this reactions and thing calculations, I have tried to describe how resonance effect came into picture. किस तरह से वो चीज resonance was defined. Resonance was defined because there was an ambiguous amount of energy difference between the theoretical and experimental values of heats of hydrogenation of benzene. If there was no resonance existing, benzene should have been cyclohexatriene and its energy of heat of hydrogenation which it was releasing should be near about 360 kilojoule per mole. Secondly, it should have alternate double and single bonds which must be localized if there is no resonance. So, localized means that one bond of benzene will be longer, the other will be shorter, the shorter one is a double bond, then the third one will again be longer, the fourth one will be shorter, and so on. So, this is not the case because of the phenomena of resonance. So, going back to the description of resonance, the second point comes that molecule is a hybrid. So, the structure I have drawn here is these two structures are canonical forms and this form is a hybrid of these two canonical forms. Now, what are these hybrid structures? Molecule is a hybrid of these structures and is not completely defined by one of these structures. The next point is hybrid is always more stable than any of the canonical form, and similar way that the hybrid was benzene not cyclohexatriene, the hybrid has a energy difference of the resonance energy, which in case of benzene was 150 or so kilojoule per mole of energy. It is called as resonance energy. The next point is that importance of resonance is more when canonical forms of similar stability are present. Like in case of benzene, we have seen two structures and those two structures are exactly similar. When they are similar and having less charges, so the contribution of the canonical forms will be more and they will be more stable towards the contribution. The next point I have mentioned here is more stable structures contributes more. If I am drawing n number of structures and there are wrong structures or there are some structures which do not follow the rule of the resonance effect, then their contribution will be less or their contribution will be minimum, negligible or maybe zero. So, I have to see the rules how I can create resonance in every molecule. So, the first of the rules, very important rules, is canonical forms must have the same number of unpaired electrons. For example, butadiene we created the positive charged and negative charged structures. So, positive and negative charge structures were allowed, but I cannot put one odd electron here. This is one electron and the other electron. So, I cannot place like this, that the number of unpaired electrons I cannot differentiate. If this was a plus, it was a minus, then it was okay, because in minus there are two electrons and those two electrons are paired up. So, this structure does not contribute to the resonating structure of butadiene at all. The second point is electrons taking part in resonance must lie in a plane. We have already discussed in case of butadiene that resonance was happening just because all the p orbitals, the black part, were sharing the electrons, and this was because of the fact that all the carbons in butadiene were sp2 hybridized. sp2 hybridization, if it is not present, if the carbon is sp3, there is no conjugation or there is a break in conjugation, the resonance effect will take place to that extent only. So, they should lie in a plane for resonance to be happening. Adjacent and opposite charges are not stable. So, I have told butadiene we have plus charge here or minus charge or vice versa, we can be, it is perfectly alright to have a resonating structure, but you cannot make this carbon and this carbon as plus and minus. As in case of ethene, this structure does not contribute to any resonance, only structure which is possible is this ethene, because plus and minus on adjacent carbons are not valid. This next point is more covalent bond structures. Why do you think that benzene is so much stabilized by the resonance effect? This is because of this point. More number of covalent bonded structures, less number of charges, less number of unpaired the lone pairs and negative charges or positive charges, less number of these charges makes the molecule more stable. So, greater the number of covalent bonds, as in case of benzene there is no charge, it is a non-polar structures both of them, so they are more stable. Greater the number, this is the most important point you will be using again and again, whichever chemistry part you are doing, organic chemistry part, you would be using this rule. Greater the number of resonating structure, more is the stability of the resonance hybrid. Identical ones are even more stable. So we can say that benzene wala case is the identical ones case because of the fact that the structures are very much similar, right. Then the point comes, negative charges on electronegative atom is more stable and positive charges on less electronegative atom is more stable. So negative charge on more electronegative atom means that if resonance has a negative charge on nitrogen in a carbon nitrogen bond, then this is more stable because of the fact that nitrogen can sustain the electronegative charge because of higher electronegativity. Higher electronegativity of nitrogen gives nitrogen in a carbon nitrogen bond, if the negative charge is on carbon, then it is less stable resonance structure or a wrong structure because it should be on the negative charges. The applications of resonance effect, I will quickly go through those thing. The carboxylic acid resonance is stabilized here, and you can say that carboxylate ions are more stabilized because of the fact that the carboxylic acid is resonance stabilized to a lesser extent. So we were talking about like the applications of resonance effect. So acidity of carboxylic acid and phenols is one topic in which you can see on the slide that carboxylic acid is showing resonance, but this resonance is having a positive charge. I have already told you that positive charge on an electronegative atom is quite of more of less contributing, so positive charge is present here. Then when this carboxylic acid or acetic acid, we are taking an example, gets converted by virtue of a loss of proton into carboxylate ion, this carboxylate ion is also resonance stabilized, like you can see in this structure. So what is happening? Carboxylic acid is also stabilized and carboxylate ion is also stabilized. So this gives for the relative the stability of carboxylate ion because of the resonance being more pronounced in case of carboxylate ions by virtue of there is no positive charge on oxygen atom. This stabilization is towards a greater extent, and this stabilization of carboxylic acid is pretty much lesser because of the presence of this positive charge, and hence the carboxylic acids are the molecules which are acidic in nature. So we would be doing this again when we would be talking about acidity of carboxylic acids and phenols. We would be discussing about this. So I was just trying to make you comfortable about the resonance effect present in carboxylate ion. Why the resonance in carboxylate ion is of a greater extent? Because of the fact two reasons are there. One, there is no positive charge on oxygen. The second reason is that this structure can be taken up as you can see that carboxylate ion is like this. You can see on my hand that carboxylate ion is present as this. So when carboxylate C double bond O, and this is O minus, and this is R group. So when I convert it to it like this, in this form I am converting the resonance resonating structures also, and I am converting the structures also. So these two are identical structures, and identical structures give more of the stability to the molecule, and hence the stabilization is towards the greater extent. So winding up with the resonance, similar basis, the phenol acidity is also given by virtue of that phenol loses one proton and gives a phenoxide ion, and this phenoxide ion is stabilized by way of resonance. You can see on the slide that by resonance these more number of structures are formed. These structures are again formed in case of phenol, but they are less stabilized because of the fact that phenol again has a plus charge on the oxygen, which is a more electronegative atom. So on this note I would wind up this session, and hope you had a good time. Thank you so much.
Dear friends, on that note, we would like to thank Dr. Khanna for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.